The following program is brought to you by Caltech.
Thanks, John. I was asked to talk about target bodies, and so I'll give you a run-through of just what we know and don't know. First of all, let's start with the terminology. John Lewis ran through most of this, so I'll just go through it quickly. A near-Earth object is defined as an asteroid or a comet that can get within 1.3 astronomical units of the sun. It's interesting to note that the population of asteroids in the near-Earth neighborhood is about 100 times that of the active comets. So it's really asteroids that we're talking about in terms of near-Earth objects. Potentially hazardous objects are a subset of the near-Earth objects in that they can get within 5/100ths of an AU of the Earth's orbit, which is about the distance a planetary perturbation can move an object in its orbit in one pass. And it appears to be about 20% of all near-Earth objects discovered. And the human mission accessible targets are generally a subset of the potentially hazardous objects. So you got this curious dichotomy of the objects that are easiest to reach are also the most dangerous. All right, so the NASA search program is outlined here. The Minor Planet Center in Cambridge, Massachusetts archives the data, does preliminary orbit determination, our program office at JPL coordinates these efforts, does precision orbit determination, uses our Sentry system to determine close Earth approaches and possible impacts within the next 100 or 200 years or so. We have the linear program near Socorro, New Mexico, run by MIT's Lincoln Lab. It's a 1-meter telescope. Catalina Sky Survey operates 3 telescopes near Tucson, Arizona. They're the front-running survey in terms of discoveries. Pan-STARRS 1 is on Haleakala in Hawaii. They're starting up as a 1.8-meter telescope. They want to build another one next to it. The NEOs infrared space observations were active in 2010. They discovered 132 near-Earth objects, 17 comets. So they provided information on the population as a whole. In fact, they've got a press conference on Thursday to announce some pretty interesting results, which I'm not supposed to mention. All right, so here's a plot of the number of near-Earth objects thought to be in the population as a function of their diameters. Let's see. This is a plot by Al Harris. One of the things you're going to hear about on Thursday is that this may not be totally correct. So, but today it's correct. If you look at the 1-kilometer sized objects, there's about 1,000 of them in near-Earth space. 140 meters, we're talking about 20,000. 50-meter sized objects, 250,000. If you get down to the sizes we're talking about, there are probably billions in the near-Earth space. So finding them is the question, of course. This is a progress report of the number of large near-Earth asteroids discovered as a function of time. These are kilometer and larger. We're up around 911 out of a total population of about 980. So we've reached the goal of getting 90%. You can see that the number of discoveries of the smaller asteroids is still rising. We haven't come close to finding that total population. This is based on optical observations, so we have to assume a mean albedo of 0.14, which may or may not be true, but if you do that, we're about 90% complete in terms of the large ones. Between 300 and 1,000, we're about 40% complete. Between 100 and 300, we're about 8% complete. And less than 30 meters, we're much less than 1% complete. So, the ground-based survey telescopes For the next generation, these are the ones that are likely to find our target body. We have Pan-STARRS 2, which is another 1.8 meter on Haleakala. They have plans for 4 co-located 1.8 meter telescopes on Mauna Kea that may or may not come to pass. That's Air Force Research Lab sponsored. That's in quotes because that was actually an earmark, Senator Inouye's earmark. PS2 is in construction, another 1.8 meter. Large Synoptic telescope is certainly being planned. In fact, it's started up. The mirror is almost complete. They still lack some funding, but it's a 6.4 effective diameter mirror, very wide field. It's designed to study dark energy matter, transient optical sky, Milky Way, and solar system science. They can't help but observe near-Earth objects, and so that telescope, when it begins operation in 2019, will be the big kid on the block and will almost certainly be the front runner in terms of discoveries. There's also a space surveillance telescope DARPA developed for improved space situational awareness, Earth orbital debris, launch. They want to observe launches, but they usually observe in the twilight regions of the day, and the rest of the night, they are willing to provide this telescope for near-Earth objects. And that'll be a remarkable asset once that comes online fairly quickly. There are space-based survey telescopes in the planning stages, both optical. The best way of doing this is the infrared, of course, because asteroids tend to peak at around 10 microns in terms of their reflected or emitted energy. There's a large synoptic telescope. You can see that it's an enormous field of view. It's a 6.4 effective meter, 10 square degrees field of view, several optical filters. They intend to survey the entire visible sky every 3 to 4 days and 2 filters for 10 years. So they will be, as I said, the big kid on the block when they get started. They have, the Pan-STARRS group has developed a very high efficiency moving object pipeline system detection software. So that's being used both by Pan-STARRS and the LSST group. So the total cost to NASA for the LSST project would be $120 million. So I mean, the total cost is far more than that, but in order to get an optimal near-Earth object survey from the LSST, NASA's being asked to pony up $120 million. Some of the issues, they won't be ready to go until 2019 or so. And of course, they're not devoted to the detection of near-Earth objects, so they could do better if they were to get rid of the pesky astrophysics goals. Space Surveillance Telescope, this is the one that's being developed by Lincoln Lab, MIT's Lincoln Lab. It's the same division that runs linear currently, but it's a much more effective telescope. It's a 3.6 meter primary mirror. First light has already taken place, but they're not operational yet. They're into a 1 year of checkout, and it's the first of 4 sites that are being planned using this design. It's an alt-azimuth mount, and it's an extraordinarily quick telescope. Point and settle time is extraordinarily quick. So some of the issues with SST are given here. As with any defense-funded operation, we have to get rid of the non-natural bodies in their images before we can process them. So that's a bit of a pain, and it slows things down. So that's the issue of the operating at classified levels. But even so, that's likely to be a big step forward for the near-Earth object program. So if we, this is sort of a differential completion versus H magnitude, which is what is usually observed. So current surveys are doing this sort of thing, and the future surveys are likely to do this. So you can see at the h equals 22, which is about 140 meters or so, there's likely to be a substantial improvement between 5.5% and 74% with the new surveys. And as you get smaller and smaller objects, the improvement varies according to size, of course. So the new surveys are going to be doing much better in terms of discovery efficiency than the current. The best survey of all would be a space-based infrared telescope, wide-field infrared telescope, located in a Venus-like orbit interior to that of the Earth. So if we assume that this is an optical telescope operational on the Earth, this is sort of their field of view. And of course, they can only observe during nighttime sky and good weather. If you're observing from a Venus-like orbit with a infrared telescope, your field of view is much larger. The confusion of background stars is much less. You're observing at 10 microns or so where the asteroids tend to peak. And unlike the optical observations, you can get diameters directly from the infrared measurements to about 10% and albedos to about 20%. So NEOWISE, which is a near-Earth object offshoot from the WISE spacecraft that was operational in 2010, actually showed sort of a prototype for this type of mission. Now, this was Earth orbital, of course, but it showed how effective near-infrared observations of asteroids can be in terms of discovery and characterizing their sizes and albedos. So it's a very powerful technique. Okay, well, I'm going to state the obvious here. Using optical data, their diameters are very uncertain. So if you talk about an absolute magnitude of 28, the diameter is 17 meters if you assume an albedo of 4%. It's 9 if you assume an albedo of 14%. It's 7 if you assume an albedo of 0.25%. Usually what we do is assume this, which is sort of a mean between these two, but it's just that. It's not very accurate. In fact, some of the results that are coming out on Thursday based on the NEOWISE data are going to improve on this dramatically. So let's assume that we have a 28, absolute magnitude of 28. For most S-type asteroids, the albedo is around 25%, so that perhaps is a 7-meter sized object. So if you just keep that in mind. This is a diagram that I think Brian Wilcox is also going to discuss. It shows the rotation period in hours versus the diameter in kilometers. So this is a rather informative slide. If an object is a rubble pile, that is, it's held together by little more than its own self-gravity, if you spin it up to about 2.2 hours, things are going to fly off. And so this is what they call the rubble pile spin barrier. And this suggests, although it doesn't prove, that most asteroids that have been looked at are probably rubble piles in this region. They're also, most binaries are located right at the boundary as well. And so the conventional wisdom then is that as these things rotate up faster, they throw off material which then agglomerates into a satellite. So that makes sense. And if you go up in this direction, we're interested. Here's 100 meters, 10 meters. So if you go up in this region here, which is what we're talking about, you get very fast rotators. Very fast rotators. And some of them are tumbling. At least some of them have been shown to tumble. And as Brian's going to point out, that makes sense because the relaxation time to principal axis rotation around your shortest axis, the time it takes to damp down to a principal axis rotation goes as the cube of the rotation period over the square of the diameter. So it's not unexpected that you would get some tumblers up here. So we're dealing with small objects, probably fast rotating, perhaps tumbling. All of that is not.
John, you want to clarify what monolithic means here?
Pardon?
You want to clarify what monolithic means?
Ah, okay. Yeah, monolithic means, actually that should be coherent rather than monolithic. It means that these objects are spinning so fast that they can't possibly have loose regolith on the surface. They would have flown off long ago. So that suggests that they're either monolithic, but actually it doesn't take a whole lot of tensile strength to prevent that. So coherent's probably a better word than monolithic here. Okay. Now I assume that our targets would be 2 meters or less. We've heard that perhaps that's not true, but let's assume for the moment that we're dealing with objects that are 2 meters and less. There are now 4 near-Earth asteroids that would be 2 meters and less, assuming a mean albedo of 0.14, and all were discovered when they were extremely close to the Earth. All are lost because they must be rediscovered during future close Earth approaches. Now, if we go to 7 meters, this is no longer the case. The Catalina Sky Survey is currently the most efficient survey. If we define a so-called entendu, which is the aperture times the field of view, which is a measure of the efficiency with which a telescope can discover these objects, you get about 2 for the most efficient current survey. LSST will be up around 321, which is 150 times more efficient. So the coming next generation surveys will be extremely efficient at finding near-Earth objects. So the number of 2 meter sized targets in 2025 may be about 600, give or take several hundred probably. And so we'll need to secure orbits during the discovery return if we're going to talk about 2 meters sized objects. And you'd really like to determine their spectral class at the same time that they're discovered, and that requires an apparent magnitude of 18 or less, or brighter, if you're going to do it with the IRTF in Hawaii. So those are pretty stiff constraints for a 2 meter sized object. Now, if we assume that 28 apparent, the absolute magnitude is 28 or fainter, or if you assume the albedo is 0.14, that means you're talking about a 7 meter sized object or less, then you can come up with a target list. And this is what I've done here. This is not meant to be completely inclusive, but it does show, I only listed the objects for which future observing opportunities exist. That is, they get brighter than 24th magnitude, and their plane of sky uncertainty is reasonable for a search. Reasonable being 1 degree, 2 degrees actually. So this one could be discovered. Well, this is the orbit condition code. If it's 1, 2, or 3, it's pretty good. If it's up around 9, not very good at all. Probably lost at the moment. But the next observing opportunity for this one, for example, is July of 2017. There are a few that have radar opportunities, not many. So that's what I'm listing here. There are a bunch if you were allowed to go up to 7 meters or so. Here's another.
Don, what's the difference between survey and non-survey?
Thanks. If there's no survey listed, that means it's likely to be rediscovered in 2022. It gets brighter than 24th magnitude, and its plane of sky uncertainty is within a degree or so. If it's not, those conditions aren't met, then you have to rediscover it. So and that would be in a survey mode. So, yeah, thanks. Oh, this is a table I ripped off from John Brophy, just showing the asteroid diameters and we also don't know their bulk densities, so it's not just that we don't know their diameters, we don't know their bulk densities. That's an issue we're going to have to deal with. I'm not sure how you're going to determine the mass of these objects before you bring them back, because traditional spacecraft tracking for an object that's that small, it's not easy. In fact, it may not even be possible to determine the mass. So you might have to wind up using a laser ranging to a disco ball that you release and let drift to the surface or something. I don't know. It would take an hour and a half. There is a correlation. Some of your C-types are in this neighborhood. Most of your S-types are in this neighborhood. M-class metals would be higher, of course. But so there is a correlation, but it's not that strong. Perhaps a factor of 1.5 or so. Conclusions. Optical photometry and IR spectroscopy are needed for determining the rotation rates, diameters, spectral class, and whether or not the object has hydrated minerals. John talked about these. There is a 3-micron band that would indicate hydrated minerals or water ice, but we're probably talking about hydrated minerals. So ideally, you'd like to get optical photometry and an IR spectroscopy and astrometry when the object is discovered, because it's not going to be discovered unless it's really close. So you got to jump on it. As soon as it's discovered, we need to jump on it with the astrometry, follow-up data for the orbits. We need to jump on it for photometry to get the rotation characteristics. We need to jump on it with the IR spectroscopy to get its spectral class. And an effort to, and the IR spectroscopy will also determine the diameter to about 10% and the albedo to about 20%. So in general, from that rotation curve, we note that the small sizes imply coherent structures and fast rotation rates. That's not a guarantee, but in general, that is the case. A few percentage of the small near-Earth asteroids could be binaries. 15% of all near-Earth asteroids are binaries, and a small percentage have been shown to be tumblers. That is, they're not rotating around their principal axis. They're tumbling, sort of like a badly thrown football. As I mentioned, the IR data can provide diameters up to about 10% and albedos to 20%. Without the IR, the albedo range could go from 0.04 to 0.6. Diameters could differ by a factor of 4, masses by a factor of at least 64, although you could make a case saying that the S-types are likely to be about 0.25, and they're not likely to have this kind of range, but if you only have an absolute magnitude and no spectral observations, then this indeed is what you're dealing with. So the mass is uncertain by a factor of 2 or more for even the best observed objects. Ground-based IR data requires an apparent magnitude less than 18, and that requires a very close approach of these objects for a 2-meter sized object, not so bad for a 7-meter sized object. Or you need an IR space telescope, but probably not the Webb telescope, because I'm told that they can't track fast-moving objects.
Now, you're saying that you've got to jump on it with discovery from the previous charts. We are discovering several of them a year or more. How practical is it to institute a program that would jump on it when you discover one that might be good target?
How practical? Well, it's certainly doable. It takes communication between the discoverers. The astrometric follow-up observations are routinely done very well, I might add, by sophisticated amateurs. The IR telescope is not, I mean, you have to book that well in advance, so that's a problem.
Give the TC 2008 TC3 example. That's a great example how fast you jump on.
Well, yeah, 2008 TC3 was a a 4-meter-sized object that actually collided with the Earth, and it was discovered 20 hours prior to impact. And the astrometry, follow-up astrometry, was provided by 26 different sites within a few hours. Really extraordinary, and so the predictions of where it would hit in northern Sudan were within a kilometer well before the impact itself. So I mean, the follow-up astrometry can be done nicely. And if we had somebody on the IR telescope, IRTF, you could convince them perhaps to take a look at this object, but it would be best to have a space-based IR telescope at your disposal. So, and radar, of course. If it's a radar target, I mean, that will nail the orbit along with the optical data on the first discovery apparition. And the radar, of course, can, if it's high signal and noise, they can get shapes and rotation characteristics. We can characterize these objects very nicely if it is indeed a radar target. Okay, so this statement only applies for the 2-meter-sized objects or less. The next generation discoveries should help a great deal. The potential target bodies in about 2025 should be, I'm guessing, this is a little more than a guess, would be about 600. The CD types that John mentioned, which are likely to have hydrated minerals, are 150 or so. 75 of, okay, so the CD types would be about 150, about 50% of them would have hydrated minerals. So, and there are still fewer targets with the IR observing opportunities. They don't get bright enough for IR observations on the ground. We'll need to secure the orbits and characterize them during discovery, optical, radar, and IR, and observe during post-discovery close approaches if they exist. And for many objects, as we just saw, they do exist. And finally, it would be nice to invest in space-based IR telescope survey, not only to find these objects, but to characterize them much better than they are now. So let me end with this. Pardon? WISE has stopped operation, of course. They ran out of cryogens. That's the prototype for what the type of telescope we'd like to have in an interior orbit. So I think it's well to point out that we're not just going for science here to a near-Earth asteroid. We're going for exploration. Science, of course, is a big driver. These objects are among the least changed objects in the solar system. So if you want to study the chemical mix and the temperature environment under which our inner solar system formed, including Earth, you'd want to study asteroids. John talked very nicely, eloquently about future space resources. And so this, in some sense, represents our future. And planetary defense, of course, we'd like to characterize these objects as best we can. Should we find an object that's on an Earth-threatening trajectory, and we have to do something about it in order to preserve our future. So thanks very much for your interest.